On January 8, 2005, the Los Angeles-class nuclear-powered submarine USS San Francisco was making its way through the Pacific Ocean about 350 miles south of Guam. The submarine was more than 500 feet below the surface. The captain had ordered flank speed, and the 6,000-ton vessel was cruising at over 30 knots, around 35 miles per hour. Then, at around 12 a.m., the submarine came to a sudden stop. One moment, it was charging through the water at full speed. The next, it had slammed head-on into something solid. The submarine had collided with a massive underwater mountain that rose thousands of feet from the ocean floor. But for some reason, it didn't appear on any of the navigation charts on board. The force of the collision was devastating. The bow absorbed the impact, crushing the forward sonar dome and buckling internal structures under the enormous stress. Inside the submarine, sailors were hurled into steel walls and equipment. 98 crew members were injured, and one sailor later died from his injuries. The accident became one of the most serious submarine groundings in modern naval history. A billion-dollar nuclear submarine had nearly been lost, not to an enemy, but because it struck a mountain no one knew was there. When investigators began piecing together what had happened, one question stood out above all the others. How could one of the most advanced submarines ever built, equipped with cutting-edge navigation systems and sophisticated sensors, crash into an underwater mountain at full speed without anyone realizing it was there? The answer reveals a challenge that every submarine faces the moment it goes underwater. Up on the surface, navigation is a solved problem. Your phone, your car, and every commercial airliner on Earth rely on GPS. GPS is a constellation of satellites broadcasting ultra-precise clock signals from orbit. When you drive down the street, the antenna inside your phone catches those radio signals, calculates the exact time delay from space, and pinpoints your location to within a few feet. But the moment a submarine submerges, that entire global satellite network becomes useless because GPS uses radio waves that are easily absorbed by water. Light also offers no help. Sunlight is absorbed and scattered by seawater so rapidly that below 600 feet, the ocean is pitch black. You can't look out a window and you can't use external cameras. A submarine commander could order the crew to use active sonar, sending out loud acoustic pings to bounce sound off the terrain ahead. But doing that is the tactical equivalent of turning on a bright strobe light in a dark room full of snipers. An active sonar pulse gives away your exact position, heading, and speed to enemy listening posts hundreds of miles away. Modern nuclear submarines do not use lights. They do not use cameras. They cannot use GPS, and they almost never turn on active sonar. They travel through the deep ocean completely blindfolded, submerged for months at a time, moving at high speeds through narrow underwater canyons. And yet, most of the time, they know their exact position on the Earth to within a dozen feet. So let's explore exactly how submarines know where they are despite being almost blindfolded. We need to look at the math behind underwater inertial sensing and how engineers turned fundamental constants of the universe into a guidance system that doesn't need to look at the outside world to know exactly where it is. To understand why underwater navigation is so difficult, we first have to answer a basic question. Why does GPS fail underwater in the first place? It comes down to classical electrodynamics. GPS satellites broadcast their signals on microwave frequencies, primarily around 1.5 gigahertz. Air is an electrical insulator. Those radio waves travel through the atmosphere and down to your phone with almost zero resistance. Seawater, however, is full of dissolved salt, sodium and chloride ions. That makes seawater an excellent electrical conductor. When an electromagnetic wave enters a conducting medium, the oscillating electric field of the wave forces the free ions in the water to move back and forth, creating electric currents. These microscopic currents act like friction. They drain the wave's energy, converting the radio signal directly into heat. We can calculate exactly how fast a radio wave dies in water using the skin depth equation. Here, omega is the frequency of the wave, mu is the magnetic permeability of the water, and sigma is the electrical conductivity of seawater. Because the conductivity of seawater is extremely high, around 4 Siemens per meter, and the frequency of a GPS signal is 1.5 gigahertz, the math spits out a skin depth of less than 1 centimeter. That means by the time a GPS radio wave penetrates just 1 inch below the ocean's surface, its energy is almost entirely absorbed. If a submarine cannot receive signals from the outside world, the crew is forced to use a method of navigation known as dead reckoning. Dead reckoning relies on a very simple concept. If you know exactly where you started, and you measure every change in speed, every direction, and every turn you make from that moment onward, you can calculate exactly where you are right now. To do this automatically, aerospace engineers build the math from the ground up, starting with Isaac Newton's second law of motion. Force equals mass times acceleration. If you know the mass of a small sensor inside the submarine and you measure the mechanical force acting on that mass when the submarine moves, you can calculate the submarine's acceleration, a. Acceleration is the rate of change of velocity over time. To get our velocity, v of t, we integrate with respect to time, where v0 is the initial velocity of the submarine when we started measuring. Velocity is the rate of change of position over time. To get our actual position, x of t, we perform a second integration, where x0 is our starting coordinate on the map. This double integration is the foundation of every inertial navigation system, or INS. If a machine can continuously measure acceleration in 3 dimensions, up, down, left, right, forward, backward, the onboard computer can integrate that raw data twice to track the submarine's position anywhere on Earth. Simple, right? But there's a catch. Consider what happens when your internal sensor has a tiny microscopic measurement error. Let's say your accelerometer reads a constant tiny measurement bias, which we'll call epsilon. The sensor thinks you are moving forward just a fraction of a millimeter per second faster than you actually are. When the computer integrates that constant error once to find velocity, the error grows linearly with time. When the computer integrates that velocity error once again to find position, the positional error grows quadratically. This quadratic growth is known as integration drift, and for those who watched the previous videos, this is another engineer's curse. If an accelerometer possesses an error so small that it mismeasures acceleration by just 1/10,000th of the acceleration of gravity, that error does not stay small. Because of the t squared in the equation, time becomes an enemy. After 1 hour of navigation, that tiny error accumulates. Your calculated position drifts away from your actual position by more than 4 miles. After 24 hours of driving blind, you are off by more than 100 miles. After a week, your computer tells you the submarine is in the middle of a deep trench when you are actually steering directly toward a shallow coastal reef. Reducing that drift isn't just a matter of building a better accelerometer. It requires solving a massive problem with the shape of the Earth itself. By the 1920s, engineers building the first mechanical gyroscopes and accelerometers hit a wall. They built precise mechanical sensors, placed them in ships, and watched the systems drift wildly out of control after just a few minutes of travel. They couldn't figure out why the math was failing. Then, a German engineer named Maximilian Schuler realized the problem. The engineers had built their math assuming the Earth was flat. In a standard laboratory on land, an accelerometer measures 2 things: the acceleration of the vehicle and the acceleration of gravity, g, pulling straight down toward the center of the planet at 9.81 meters per second squared. If your vehicle stays level on a perfectly flat surface, the horizontal accelerometer reads 0, exactly as it should. But the Earth is a sphere. As a submarine drives forward along the curved surface of the Earth, The direction of down, the invisible vector pointing toward the center of the planet, continuously changes angle in space. If a submarine drives forward for 60 miles without tilting its internal sensors down to account for the Earth's curve, the horizontal accelerometer is no longer perfectly perpendicular to gravity. Gravity begins to leak into the horizontal sensor. The accelerometer registers a tiny component of gravity, g times sine of theta, and mistakes it for forward acceleration. The computer integrates that false acceleration twice, and the navigation position drifts into chaos. To fix this, Schuler asked a theoretical question. Is it possible to build a sensor that is completely immune to the acceleration of the vehicle? A sensor that always points toward the exact center of the Earth, no matter how fast the vehicle moves. Schuler turned to the math of pendulums. A simple pendulum consists of a mass on a string of length L. The time it takes for that pendulum to swing back and forth, its natural period of oscillation, t, is governed by this formula. If you put a normal pendulum inside a car and slam on the gas pedal, the mass swings backward. The horizontal acceleration disturbs the pendulum. Schuler realized that if you wanted a pendulum that would never swing backward when the car accelerates, a pendulum that would always point straight down toward the center of the Earth, the string length would have to be equal to the distance from the surface of the Earth to the center of the Earth. The string length L would have to equal the radius of the Earth, r, which is roughly 6,371 kilometers. If you plug the Earth's radius into the pendulum equation, the math gives an exact time, 5,063 seconds, or 84.4 minutes. This is the Schuler period. Funnily enough, this is the exact same amount of time it takes a satellite to orbit the Earth at sea level. You cannot build a pendulum 4,000 miles long, but Schuler proved that if you design a mechanical gimbal system or program an electronic feedback loop so that its internal control loop oscillates with a natural period of exactly 84.4 minutes, the system behaves as if it were suspended from the center of the planet. When the submarine accelerates, the horizontal force pushing on the sensor is perfectly canceled out by the simulated pendulum dynamics. Gravity can no longer leak into the horizontal measurement. This discovery, known as Schuler tuning, moved inertial navigation from a theoretical novelty into an operational military technology. It allowed early submarines to stay submerged for hours without their navigation systems blowing up from gravitational errors. But mechanical systems had a new problem: moving parts. Early inertial navigation systems relied on mechanical gyroscopes, spinning metal flywheels mounted inside complex three-axis gimbals. These flywheels spun at thousands of revolutions per minute on mechanical bearings. No bearing is frictionless. Over days of continuous operation, microscopic friction in the gimbal pivots generates heat and creates tiny unwanted torques. These torques cause the spinning flywheel to precess, to slowly wobble out of perfect alignment. This mechanical drift meant that every few days, the submarine had to come near the surface, extend a periscope or radio antenna, and reset its navigation computer using a star sight or early radio beacons. For a nuclear submarine whose only defense is staying hidden deep underwater, having to surface every few days to fix the navigation defeats the entire purpose of being a submarine. If a crew wanted to stay underwater for 6 months at a time, engineers had to get rid of the spinning wheels. They started to measure motion using light. In the 1970s, aerospace engineers created a device called a ring laser gyroscope. They hollowed out a triangular channel inside a solid block of glass and fired 2 lasers in opposite directions around the loop. This relies on a physics principle called the Sagnac effect. Because light travels at a constant speed, if the submarine turns, the laser traveling with the turn takes slightly longer to complete the loop than the laser traveling against it. By measuring that microscopic time difference, the submarine knows exactly how fast it is turning. In a ring laser gyroscope, the glass block acts as a resonant cavity for two counter-propagating laser beams. Instead of measuring a shifted French pattern on a screen, the two laser beams inside the glass block combine to form a standing wave of light. When the submarine turns, the physical glass block rotates around that standing wave of light. Optical sensors built into the glass block count the bright and dark nodes of the light wave passing by. Because the wavelength of light is extremely small, less than 1 micrometer, a ring laser gyroscope detects rotation rates as slow as 1 revolution every few years. There were no bearings to wear out, no flywheels to balance, and no mechanical friction. But as engineers built the first production laser gyroscopes, they hit a fatal optical flaw. When the submarine turned very slowly, the rotation rate dropped near zero. At these low speeds, a tiny fraction of the light from one laser beam scattered off microscopic imperfections in the mirrors and mixed with the opposite laser beam. This backscattering caused the two laser beams to lock on to the exact same frequency. The standing wave collapsed. This phenomenon, known as laser lock-in, created a massive dead zone. When the submarine made slow, gentle turns, the laser gyroscope went completely blind. It registered zero rotation when the ship was actually turning. To solve this, engineers came up with a bizarre mechanical solution: mechanical dithering. They mounted the entire multi-thousand-dollar glass laser block on a central piezoelectric spring. A motor physically shakes the entire laser block back and forth, vibrating it thousands of times a second at high frequency. By constantly shaking the gyroscope, they force the system out of the lock-in dead zone. The computer subtracts the known vibration of the motor, leaving a clean, precise measurement of the submarine's actual rotation. They built a system where lasers measure the behavior of light, while a crude motor shakes the sensor violently to keep the light from breaking itself. By combining 3 ring laser gyroscopes with 3 quartz accelerometers on a Schuler-tuned platform, engineers created the modern electromechanical navigator. For the first time, a nuclear submarine could dive underwater in Connecticut, travel thousands of miles under the Arctic ice cap, and emerge weeks later in the Pacific Ocean with its navigation computer off by less than a few hundred yards. The science we've mapped out here, RF skin depth, double integration, Schuler tuning, and the Sagnac effect, are not secret formulas anymore. They represent universal laws of nature. Every major naval power on Earth uses them. You find these same fundamental principles applied in the navigation suites of American Virginia-class attack submarines, Russian Bory-class ballistic missile ships, and British Vanguard-class deterrent vessels. All of them rely on ring laser gyroscopes and quartz accelerometers to navigate in the dark. But no matter how precise your optics are, no inertial system is perfect. Over weeks and months at sea, microscopic errors still accumulate. Integration drift never sleeps. Eventually, a submarine must update its position. Surfacing to catch a GPS signal exposes the ship's sail to radar satellites and maritime patrol aircraft. So modern navies developed a way to reset their position without surfacing: gravity gradiometry. The Earth's gravitational field is not uniform. Dense underwater structures like basalt mountains, oceanic trenches, and heavy iron deposits create tiny local variations in the strength and direction of gravity beneath the hull. As the submarine glides through the water, these sensors continuously measure the microscopic changes in the gravitational field beneath the hull. The onboard computer compares these live gravity measurements against the high-resolution map of the seafloor's gravitational field stored in its memory bank. If the computer measures a specific gravitational bump, it matches that bump to the digital map, instantly resetting the double integration drift without emitting a sound wave or exposing an antenna above the water. And the technology continues to evolve. Engineers are currently moving beyond laser gyroscopes toward the next frontier of guidance physics: quantum cold atom sensors. Inside a quantum navigation system, lasers freeze a cloud of rubidium-87 atoms down to a fraction of a degree above absolute zero. This extreme cold forms a state of matter known as a Bose-Einstein condensate. At these extreme temperatures, the atoms stop behaving like solid billiard balls and begin behaving like quantum matter waves. By splitting and recombining these atomic waves using laser pulses, physicists create atomic interferometers. Because atoms possess mass, they are millions of times more sensitive to acceleration and gravity than weightless photons of light. A quantum inertial navigation system will allow submarines to travel underwater for an entire 6-month deployment without drifting by more than a few meters, rendering external navigation signals permanently obsolete. The story of underwater navigation evolved from sailors guessing their location with magnetic compasses into a high-stakes arena of computational optics and quantum physics.